11H, integration by recognition. Today we are learning about integration by recognition to antiderive unknown expressions. What you need to be able to do is differentiate various expressions, recognize the similarities between the differentiated expression and expression to be integrated, and then use this similarity to integrate expressions. So basically what we're doing today is we are going to integrate by recognition, which means there's no specific rule for the functions that we're trying to integrate, but rather we're going to try and figure out similarities between the function that we want to integrate and between a previously differentiated function, because differentiating and integrating are opposites. There's basically two parts to it. So the first part, what we want to do is they'll give you a function to derive. Now, if you think about it, we know way more rules as to how to derive functions than to antiderive. For example, you know the product rule, you know the chain rule, the quotient rule, you know all of these that we don't have a version of them in integration. So if they ask you, for example, to integrate this, well, we can't do that, but we can derive that. And deriving a function, a specific function that they give you, can actually help you integrate a function that looks like this. Then, once we've derived that function, we're going to integrate a function that is unknown, but it has some sort of a similar function to the similar aspect to the function that you just derived. A lot of the time, you will be required to substitute, and that's basically how you do it. You will be substituting in. So I know this sounds kind of confusing. Let's go ahead and complete an example, and I'm sure it'll be a lot clearer once we do that. So here's a very simple example as to how this works. Differentiate x e to the power of x. So we have a rule to differentiate that. We don't have a rule to integrate it, say just in case they ask me to integrate that. So how do we differentiate this? Well, we need to use the product rule. X will be my u and e to the power of x will be my v. So when I differentiate x, I get 1. When I differentiate v, I get e to the power of x anyway. And then with the product rule, what we do is we multiply across. So I get xex plus e to the power of x. So what does this tell me? This tells me that when I derive my function exe to the power of x, I get this here. Why is that so important? Well, what is the opposite of differentiating? It's of course integrating. So what this also tells me that if I were to integrate this function, I would get xe to the power of x. So this is moving forwards whilst this is moving backwards. So you might see where we're going with this. Now, when it says part B, hence find an antiderivative to xe to the power of x. Again, we don't have any kind of rule to be able to do this. But what we do know is this relationship between our two functions. So xe to the power of x is equal to xe to the power of x plus e to the power of x. What I will do is I'm going to separate this out so that we can isolate the part that we need. Now, again, I'm just going to quickly point out, I'm going to do this only once. It runs throughout the whole thing. It says find an antiderivative, so we don't necessarily need the plus c, because the plus c that I'm going to assign is just going to be 0. If you want to, if you want to include it, go for it. Okay. Hence find an antiderivative to xex. So what is it that I actually want? And this is always a really good thing to write so that you can recognize the part that you need. I want this. I want the antiderivative to xex. Can I see that anywhere in the function that I've just written? Yes, I can. That's this part. I could see that. So what I want is the antiderivative to xex dx. So if this is what I want, this is what I need to isolate. Everything else needs to go to the other side. So on the other side, I already have xex. And what I'm going to do is I'm going to subtract this. Whatever I do to one side, I have to do to the other. So that'll be minus the antiderivative of e to the power of x, and that should equal xex dx. All right. Now, why did I do that? Well, on this side, this function's already completed. I don't need to do anything to it. And this one is a very easy function to integrate. So the s derivative of ex is just e to the power of x equals the antiderivative of x ex dx, which is exactly what I want. It's asked me to find the antiderivative or an antiderivative of x e to the power of x, which is what I've just done, x e to the power of x, and that is equal to x e to the power of x minus ex. And that's it. That's how you complete it. So what I've done here is, first of all, I've derived it, and then I have written out the relationship between the two. I've then isolated the part that I want. I've taken over everything else to the other side. I've then completed whatever operations I need to do. In this case, I just needed to integrate it. And finally, I have my answer here. Now, we're going to do a bunch of these today, so don't stress if this seems confusing or overwhelming. We're going to do quite a few to go over. Next, example 24. Differentiate y equals log e cos x. Again, this is a function that I can differentiate. If you kind of look at part B, what we're trying to get to is they want us to find the antiderivative of tan x, which we don't know how to do. So that's why I need to use this function that they've given me to help me find this antiderivative. Okay, let's start off here. So differentiate it. So, actually, it's not product, it's the chain rule. So we want the derivative of the inside over the derivative of the outside. So I always like to write d by dx is equal to log e cos x is equal to, so we want the derivative of the inside, so the derivative of cos is negative sine over the function of the inside. So that's cos x. So we're using both the chain rule. Sorry, I know I kept saying chain rule. It is the chain rule, but it's actually just the log function chain rule. So if you remember log e g of x, the way we do this is the derivative of the inside divided by the function of the inside. So chain rule, but specific to the log function. Okay, when we differentiate that, that'll equal negative tan x. Hopefully you can see where we go for part B here. So I'm just going to quickly write the relationship between the two. So as we know, the derivative of log e cos x is equal to negative tan x. So if I were to go backwards, that means the antiderivative of tan x would be equal to log e cos x. Now, when they say hence find the antiderivative of tan x, what do I want? I want tan x. So I'm going to quickly write this out here, and I'm going to highlight the part that I want. So I want this part. What's in the way? Just this negative. So of course, when you have a constant, what you can do is you can take it out of the integral. So you would just have the negative out the front there. So the way I'd get rid of that is just by dividing both sides by -1. So that gives me the antiderivative of tan x is equal to, that should be negative log e cos x. Kind of wrote that a bit messy. Let me try that again. Negative log e cos x. Again, differentiate this. This time we're using, once again, that log rule, so the chain rule plus the log rule. So what we have is we have the derivative of the inside over the function of the inside, so dy by dx. What's the relationship between the two? I might write that in part B because that's what I need to do anyway. So what happened was when I differentiated log e x squared minus 2, I got 2x on x squared minus 2. So what's the relationship? When I integrate 2x x squared minus 2, I get log e x squared minus 2. Now you might want to start getting into the habit where you automatically write constants on the outside. Like before we had the negative, I could have written on the outside. Here I have the 2, I could have written that on the outside. So you might want to start doing that if it helps you to kind of separate it out. Because what is it that I want? Well, I want the antiderivative of x squared minus 2. Can I see where that is? Well, that's that, and I want this part. What's in the way? The 2. I want to get rid of that. Because it's a constant, I can just divide both sides by 2. So I get a half log e x squared minus 2 is equal to the derivative of x on x squared minus 2. Now this one's a little bit more of an application, because now it says find the exact area bound by that particular graph, the x-axis, x equals 2, x equals 4. Check your answer on your calculator. So what we should always do, of course, is graph whenever we're about to find the area, just in case it goes below the axis. This function, it's not a function that we're familiar with, but it does look like this. So it's got an asymptote, it's not going to fall below the axis. Here would be 2, here would be 4. So what I'm trying to do is I'm trying to find this area over here. So what it wants is x minus 2, and it wants it between 2 and 4. Now, of course, we don't know how to find the antiderivative of that, but we actually have done that in the previous question using recognition. So the answer is a half log e x squared minus 2. And that will be bound between 2 and 4, because that's the two boundaries that I need for my area. All right, now from there I can just work as normal. So I'm going to go ahead and start substituting. So that's a half log e 4 squared minus 2. 4 squared is 16 minus 2 will be 14. Minus a half log e 2 squared is 4 minus 2 is just 2. Then really all that we can do to simplify this is divide. So that would be 14 on 2, which is 7. Because it's the area as well, we'd write units squared. All right, the rest of the examples are practice exam questions. So what I would suggest that you do is at this point, pause the video and give these questions a shot. I am going to go through them anyway. So if you need any hints or any help, come back to it, or when you've finished it all, come back and watch just to make sure that it's all correct. Sorry, I just realized as well, it does say check your answer on your calculator, so you can go ahead and do that yourselves. All right, question 26. This is from the 2012 exam. F b r to r, f of x equals x sine x, find f dash of x. So as soon as we have something like this that we know we can't integrate and they want us to differentiate it, we can always almost picture that they're going to then ask us to antiderive it through recognition. All right, u is equal to x, v is equal to sine x, u dash is equal to 1, v dash is equal to cos x. Multiply it out, so that means the derivative of x sine x will equal to x cos x plus sine x. I'm just going to copy that over for the next part. All right, so what it now that says is use the result of part A to find the value of this in the form a pi plus b. So that's just to help me there with my answer. There's a couple of parts of this. The first thing is it wants me to integrate x cos x, which I can't do, and then I will need to substitute in the boundaries. But the fact that they've given me this for part A indicates that I should be able to recognize something in here that is similar to this. Then once I have an integral for it through recognition, I can then go ahead and sub in the boundaries. So let's paste our relationship. So we know that when I derive x sine x, I get the derivative of x cos x plus sine x. So let's go backwards. If I go backwards, what do I get? I get, if I integrate x cos x, and I'm just going to separate them out straight away just to make my life a little bit easier down the track, I end up with x sine x. So the antiderivative of x cos x plus sine x is equal to x sine x. What is it that I want? Well, it's this blue highlighted part. So I want this. Let me just fix this up to be in black. Makes it look a little bit easier. I want this, the x cos x part, including the dx. So if that's what I want, isolate it. Everything else goes to the other side. So this is what I want. Everything else goes to the other side. So to the other side, I'll have x sine x minus the antiderivative of sine x, which is equal to the integral of x cos x. Let's antiderive that sine x at first. So when I antiderive sine x, I get negative cos x, so that'll be plus cos x, and that's equal to the integral of x cos x dx. So that's great, that's exactly what it is that I need. Of course, I need to put in my boundaries now, so that'll be pi on 6 on pi on 2. And that means I can chuck in my boundaries here, and I can go ahead and substitute my values in now. So that'll be pi on 2 sine pi on 2 plus cos pi on 2, and then minus pi on 6 sine pi on 6. Of course, minus again. If you're unsure of this, make sure you put in your brackets. Don't do it right away. Cos pi on 6. All right, now it's just a matter of working out our values. So sine pi on 2 is 1, so that'll end up being pi on 2, plus cos pi on 2 is 0, minus sine pi on 6 is a half, and a half times pi on 6 is going to be pi on 12, minus cos pi on 6 is root 3 on 2. Putting that all together, what you can do is just make everything over the same denominator. It's probably the easiest way to go. So that'll be times 6, and let's add that all together. So that'll be 6 pi minus 1 pi, so it'll be 5 pi, minus 6 root 3. Can't really do much with that. So that's 5 pi minus 6 root 3 on 12. Now we're almost there, but the question has specifically asked us that it wants our answer in a pi plus b, so not in fractional form. So I need to separate that out. So that'll be 5 pi on 12 minus, and the 6 and 12 can cancel out to give me on 2, root 3 on 2. All right, next question. This is a multiple choice, so we've got parts of the graph with the equation y equals e to the power of x and y equals 2 are shown here. The total area bounded by the y-axis, the line y equals 2 and the curve of the equation is given by whichever one of these. So what I can see here is I need to find this particular area. Now that looks pretty strange because what we're used to is finding the area underneath the curve. So if I had this curve, usually I'd be able to find the area that's over here. But that's not what I want. I want the area that is bound between this line. We can kind of separate this. We haven't done this exercise yet, and so I think it's the next one where we're finding the area between two curves. I know it's a line, but it still can be called a curve in this case. So what we're doing is we're finding the area. Let me go to straight lines. It's as though we're finding the area here of this particular rectangle. And then hopefully you can see if I were to subtract the area that is underneath this curve, I would end up with that area in between. So I can do that, minus, and that's the red curve, minus that area. And that should equal this grey area in between. So that's exactly what I need to do. The area underneath this curve minus the area underneath that curve. So what are these two curves? Well, this one is just y equals 2, and this one is y equals e to the power of x. Our last problem is, well, where do I integrate it between? So I know I start off at 0, but what is that value? Well, I know that this is the curve y equals e to the power of x, and the y value here is 2. So I just need to substitute that in, and from there I can find my x value. So 2 is equal to e to the power of x. To get x by itself, just take the e over. So that's log e2 equals x. So that's your specific x value. So what do we have in total? I'm going to integrate between 0 and log e2. I'm going to integrate my curve, well, it's actually the line, whereas y equals 2. Then I'm going to subtract the area underneath the curve of e to the power of x. That's all dx. You can see here that that is part D. All right, we're almost there, so this is the last question now. We've got the graph of x log ex is shown below. Find the derivative of x squared log ex. And as we can imagine, we're probably going to get to the point where they ask us to integrate this, which is why they've given us a derivative that's going to help us with that. We're going to need to use the product rule here. So u is equal to x squared, v is equal to log ex, u dash is equal to 2x, v dash is equal to 1 on x, and you just multiply across. So x squared times 1 on x, the x's will cancel out, so that'll just be x, plus, and then that'll be 2x log ex. So what have we just discovered? It's that the derivative of x squared log ex, I had to squish that in, is equal to x plus 2x log ex. Now we can imagine that in the next part we're going to have to use that. So I'll copy it across. Now it says use your answer to part A to find the area of the shaded region in the form of a log e b plus c, where a, b, and c are non-zero real constants. So what we're doing is we're finding the area of the shaded region. Of course, when we need to find the area, we need to set up an integral. So what is it that I want? I want to integrate between 1 and 3 of this curve. So the curve is up here, x log e, x dx. That's what I want. Obviously, I can't do that. There's no such thing as like a product rule for integrating, but they've given me this part in the hope that I can recognize something similar and rearrange my function to help me do that. So what's the relationship that I've just found? I found this relationship, and on the side, I'm just going to write what it is that I want. That was log ex. Okay, I'm just going to make this a little bit clearer because it looks a bit, I don't like it very much. Oh my goodness. What have I done just for a little bit of aesthetics? There we go. All right. So what is it that I want? I want, or a part of what I can recognize is this, the x log ex. Hopefully you can kind of see that. So I'm just going to quickly set this equation up. What do I know? I might start off with here. When I integrate x, and when I integrate, I'm going to pull the 2 out straight away. So this is what I meant by pulling out the constants, because it'll help you. When I integrate both of these, or and differentiate it, I'm going to go backwards. So I'm going to get x squared log ex. So what is it that I want? I want this part here. That's what matches this. Of course, I want the boundaries as well, but I'll put that in a sec. Everything else needs to go to the other side. So the x squared log ex is already there. Take over the antiderivative of x, and then I'm going to divide everything by 2. So firstly, take this over. Secondly, take that over. So I'll just chuck that in at the front. That's a half, dividing everything by 2. When I take that all over, what am I left over with? The integral of x log ex, which is exactly what I want. Now, before I go in and put my boundaries, I'm just going to antiderive this. So antideriving x, I get x squared on 2. And of course, I've already got a half there on the outside, so that becomes 1/4. So that'll be minus 1/4 x squared. And that will be the integral of x log e dx. Now the last thing I need is my boundaries, so I'm going to go ahead and put them in. So that's between 1 and 3, 1 and 3. Sub it all in, so it'll be a half. 3 squared is 9. Again, 3 squared is 9. Minus, be careful now with your negatives, so put in the 1. 1 is for x squared is just 1, log e 1, and then because it's already a minus, minus becomes a plus, so 1/4 times 1 squared, which is 1. All right, simplify this as you can, so that's 9 on 2 log e 3 minus 9 on 4. Log e 1 is just 0, and then plus 1/4. Can we do much to simplify it? Well, that'll just be 9 on 2 log e 3, and then minus 9 on 4 plus 1 on 4 will be negative 8 on 4, which is just 2. And because it's area, it's units squared. And that's it for this exercise. Hopefully you've got the hang of it. It is a little bit tricky, but as you can see, it does pop up in exams quite often, so it is something that you need to practice. Please go ahead and complete the questions from exercise 11H.